Hello. Today we're gonna try something different with how to present solutions. So, can everyone open their chat and open the link? Yeah, right in the first slide if you want to. If anyone's having difficulties, then make sure to let me know. Yeah, I'll wait for a few more seconds, I guess. Yep, so today we're gonna be doing geometry again. Hopefully you guys can see the slideshow. So to start with, we have terminology to do with circles. Today's lecture will be on circles. So at the bottom left, you can see an image of a circle with a chord, radius, diameter, and other stuff. So the definition of a circle is a set of points that are a specific distance from a specific point. That point is the center, and the distance is the radius. As you can see, the radius is a line segment from center to a point on the circle. The diameter is a segment from 2 points on the circle that passes through the center. A chord is just any segment from 2 points on the circle. And a tangent is a line that touches the circle at one point. So at the bottom right, there's some problems. Have a go. You can ask me for help if you want, by the way. Okay, preferably write the answers to me in the Zoom chat, but yeah, this is fine if you want. Doesn't matter. But yeah, that is right, whoever wrote that. Yeah, maybe have like 2 more minutes. We try the problems. Okay, hopefully you guys have had enough time to try the problems. I'll go over the solutions now. So for problem 1, it should be quite simple because the diameter is a line segment from 2 points with some more specific conditions. So it is a line segment from 2 points, which is the definition of a chord. Okay, for problem 2, most of you sent correct solutions. Those who did send solutions got it correct. If any of you want to present, then you can let me know. Okay, I guess not. So we have a circle and a line. This line is a tangent. The problem tells us that. And then this is the center. We want to prove that these two lines are perpendicular. All right, so most of you got it right. You assume if it isn't perpendicular, right? If this angle is not 90 degrees, let's make the diagram a bit worse. Yeah, okay. If the angle is not 90 degrees, then we draw a perpendicular line. However, this line, okay, O, A, B, okay, A is where the tangent touches the circle. And then you draw a perpendicular line from O to the tangent. And then OB is shorter than OA. So that means B is inside the circle. But that doesn't make sense because it's meant to be a tangent, so it's never meant to be inside the circle. So therefore, the initial assumption that the angle is not 90 degrees is incorrect. So the angle is 90 degrees. Question 3, I don't think any of you guys reached this, but hopefully you guys at least had a go. Okay. Hold on, I'll change the screen share. Can you guys see the Jamboard? Question 3 was prove that if a line touches a circle at point A and that line is perpendicular to the radius, then that line is the tangent. So again, we do a similar type of proof. For any line, for any other point on the tangent on this line, that line, like for example, for any point B on the tangent, OB is bigger than OA, so B is outside the circle. And so the line never goes inside the circle, and so it is a tangent. It only touches at point A, and every other point is outside the circle. So that's it for these 3 problems. I'll change my screen share back. Okay, next slide. There's more terminology to do with circles. As we can see, an arc is a part of the circle between 2 points. The sector is like a 2D part of the circle between 2 radii, and a segment is another 2D part, but it's like bounded by a straight line in the circle instead of 2 radii in the circle. So one more problem. This one should be quite short. So is a circle A, C, D. The center is A, and C and D are the 2 blue points. The label is a bit tiny, sorry. And what are arc CD, sector CD, and segment CD? Guys, get a minute. Oh, by the way, for the Jamboard, you can change slides at the top if you guys didn't notice that. Okay, hopefully that's enough time. I'll swap my screen to Jamboard. Okay, this question was a bit of a trick question. So firstly, we have arc CD, right? An arc is just a part of the circle between 2 points, and we said that the 2 points are C and D. But it's a bit, right, there's two arcs here. It's a bit ambiguous. Both of these are arc CD. So the way to distinguish them is major and minor arc CD. The major is the bigger one. So the one on the left is the major arc CD, and the one on the right is the minor arc CD. Similarly, there's also multiple sector CDs and segment CDs, but they follow the same kind of logic. You guys can have a think about that for a few seconds. Yep, so again, we have two sector CDs. This one that I'm coloring in right now is minor sector CD, and this one is major. And for the segments, again, you have two possible segments. This one is minor, and then the other one is major. Okay, next slide. Here's a problem. A circle with center A. DCE are points on the circle. And we know angle CDE is 40, and we want to find angle CAE. Oh, by the way, if you guys are unsure about anything, make sure you ask. Yep, many of you got the solution already and are saying that CAE is the angle at the center, but try to prove it like without just using basic geometry. But yeah, that is true. Okay, 1 more minute. Okay, hopefully that's enough time. We'll switch to the Jamboard. And by the way, I've swapped the third slide. of the Jamboard. This is what we had, and we knew this was 40. Yep. Okay. Jackie, do you want to present? You can draw.
Okay. Well, from there, I drew a line in the middle to the side, and I set that value as like x. Yeah, I set that value as x. And then the other one as like 40 minus x. And since these are isosceles triangles, the bottom angle would be x as well, and that one would be 40 minus x. And then I added a line, and the bottom two angles should add up to 140 because angles in a triangle add up to 180 and the top angle is 40. And if I add these two together, they add up to 40. So then that means that these two are 100 degrees, and thus that angle is 80. Yeah.
Yep, that's perfect. Another way to go about it is to calculate those two angles, and then you know that those three sum to 360. But yeah, your solution is great. Again, if anyone has any questions, make sure to ask. Other than that, that solution was great. I don't need to present one. Okay, next slide. Alright, this is the theorem some of you guys used when you guys got the answer. And now the problem is to try prove it for general cases, right? For any angle, not just 40 degrees. Again, like 2 or 3 minutes. It should be very similar. Okay, so this theorem is true for any point C between A and B on the same arc. So like either the major arc AB or the minor arc AB. So C could be anywhere between A and B. And that's where difference is compared to the last question. You guys can think about it if you want. 1 more minute. Okay, time's up. We'll move on to slide 4 of the Jamboard. So most of you got most of the proof, but there's something that is quite difficult to notice if you've never done this before. Okay, so I think I'm sharing the Jamboard. We'll move on to slide 4. So here's the configuration. We got A, B, C, and O. Alright, and then most of all of you did a similar proof than last time, where you did that X and Y, and then you got X plus Y using some isosceles triangles. However, something that you guys did not consider. Okay. So in this proof, what did we do? We did ACO is equal to X. Right, this is a let, and then let angle BCO equal to y. And we know AO equals CO equal BO because they're radii. So then we know AOC and BOC are isosceles triangles. And then we know angle CAO is equal to x and angle CBO is equal to y. And then angle AOC is equal to 180 minus 2x. And angle BOC is equal to 180 minus 2y. And then now what you guys did is angle AOC plus angle COB plus angle BOA is equal to 360. All right, this seems true, this last line. However, remember that C can be anywhere. So for example, imagine the C. Okay, let's call this C2 and C1. Then, all right, we got AOC. I'll change colors. This is angle AOC. And this is angle COB. And then angle BOA is here. So that last line is no longer true, and we cannot assume it. However, looking at this diagram, it's quite an easy proof again. Right, very similar. I won't go over it. We'll go back to the PowerPoint. By the way, the name of this theorem is the inscribed angle theorem. I think. I'm not sure. I don't learn names. Yeah, just if you want to know. Okay, and now we have two problems. Yeah, the points are a bit unclear on the diagrams. The first diagram in clockwise order, we have CAB, where C is the point on the left, and A is the point that looks like a right angle. And then on the second diagram, point A is at the top, and then point C clockwise, going clockwise from A, and then B. Oh, and also, if you don't remember from last lesson, the orthocenter, H, is where the altitudes intersect, where the altitudes are perpendicular lines from the vertices to the opposite sides. And O is the circumcenter, which is the center of the circumcircle, which is the circle that contains the 3 points of the triangle. By the way, problem 1 has 2 parts. Right, the first one is if it's 90, then it's a diameter. The second part is if it's a diameter, then it's 90. You guys can have 2 more minutes. Okay, try the problems for 30 more seconds, I guess. Okay, hopefully you guys have had enough time. I'll present the solutions now. We'll move on to slide 5. Draw an O to the A. Okay, so question 1, we have O and then A. Oh no, that's C, A, B. And first part of the problem was if BAC is 90 degrees, then prove BC is a diameter. Alright, so okay, let's say this is our right solution. if angle BAC is 90, then angle BOC is 180 because it's double. It's the angle at the center. So therefore, since BOC is 180, BOC are collinear. They're on a straight line. So by the definition of a diameter, BC is a line segment between 2 points on the circle, and it passes through the center. So therefore, BC is a diameter. For part 2 of the problem, we know that BC is a diameter. Oh, by the way, quite a few of you had very weird and circular solutions for part 1. Or part 2, I forgot. But just do this. Part 2, if BC has a diameter, then that means BOC are collinear. They're on a line. So BOC is equal to 180. Therefore, angle at the center is double angle at the circumference. So BAC is 90. That's it for that problem. We'll go on to the next slide. This problem was a bit more difficult. We have A, B, C as the circumcenter, and as the orthocenter. And the question was, we want to prove WTP, that angle BAH is equal to angle CAO. Okay, so immediately I feel like, okay, so you just try to find these two angles, right? Probably the most logical way to find BAH is BAH is equal to BA, again at this point BD, equal to angle PAD, which is equal to 90 minus angle APC. And angle CAO is equal to 180 minus angle AOC over 2. Because O is the circumcenter, so it's equidistant from the 3 points. So AOC is an isosceles. And AOC is equal to 2 times angle ABC. Therefore, CAO is equal to 90 minus angle ABC. Then we notice it's the same thing, set it equal. That's how you solve this problem. Supposedly just working backwards, I guess. Not really, kind of. Just like do the problem. Okay, we'll go on to the next slide. Okay, we have circle center A and points C, F, D, E. And we want to prove, okay, we know that angle CDE is 40 and we want to find angle CFE. Again, some of you might know ways to solve this instantly by quoting theorems, but try to prove it using basic geometry. Okay, one more minute. Okay, hopefully that's enough time. This problem is quite easy if you make the important insight, and that is, yep, we use the theorem we just learnt, and that is the inscribed angle theorem. Angles CFE and CDE are both half of angle CAE, so therefore angle CFE is equal to angle CDE. So it's equal to 40 degrees. I'll write that on the Jamboard, but it's quite a quick proof. Okay, next slide. This is the theorem. I have no idea what it's called. And to prove it, we just do the same thing. Angle CFE and CDE are both half of angle CAE, so they're equal. Any questions? Okay, next slide. So now we have cyclic quadrilaterals, and the definition of a cyclic quadrilateral is a quadrilateral with all 4 points on a circle. As long as there exists a single circle that has all 4 points, then the quadrilateral is cyclic. And there can only exist at most one, by the way. You can't have two circles that both go through 4 points. You can prove that if you want to. So now we have a few problems. Alright, ABCD is the cyclic, and BAD is 75, and BAC is 40. I'll write the question on slide 7 of the Jamboard if you guys can't see it that clearly. And feel free to share me your answers in the chat if you guys solved it. Okay, you guys can have 1 more minute. Okay, we'll start presenting solutions. Track here, if you want to present, you can start drawing on slide 7.
Okay. Slide 7.
Yep. You can use the diagram if you want to.
Oh, I see. Okay. Well, if that angle's 75 and that angle's 40, and then what are the terms? BDC. I just added a line through there. And then that angle will be 40, as we kind of learned that theorem before, that if these are like the same line and the third point is all on the triangle, then these two angles would be the same. And then this angle would be 35. Well, for the second part, this angle would be 35, and therefore that angle would be 35. And since angles in a triangle add up to 180, that angle would just be 180 minus 35 minus 40, which is 105. And yeah.
Yep, perfect. Another thing to consider is a cyclic. Okay, so we'll move on to slide 8. Here we have A, B, C, and D. Alright, the inscribed angle theorem states that for any 2 points, for example C and D, for any other point, like A or B, the angles are equal. However, A and B are both on the same side of DC. For example, if point E was here, angle DEC is definitely not equal to angle DAC or DBC. But for example, if point F was here, then DFC is equal to DEC. Right, it has to be on the same arc. A and B are on the major arc, and F and E on the minor arc. Okay, so some of you might have noticed that in the previous question, BAD plus BCD is 180, and that is not a coincidence. Opposite angles in a cyclic way sum to 180. Alright, so if we move back to this example, we can prove if 2 points, for example A and E, are on opposite sides of D and C, then they sum to 180. We could use the way Jackie used, which is add line AE, and this angle is equal to this angle is equal to this angle. Another way is we consider the center O. And then we have DOC is equal to 2 DAC. Right, this DOC. So then the other DOC is equal to 360 minus 2 DAC. And that's equal to 2 DEC. Right, we just use the inscribed not the inscribed angle, the other theorem, the angle. Yeah, well, that's the inscribed angle theorem. Oh, my bad, guys, I'm tripping. Okay, so we have the angle at the center and E, which is on the circle. So we know DEC is equal to half of this angle, which is equal to 180 minus angle DAC. Okay, we'll move on to the next slide. Okay, so this is just a generalization of the last problem. Right, ABCD is cyclic, ABC plus ADC is 180, and ABD is equal to ACD. And it works backwards as well. So if any of those are true, then ABCD is cyclic. And if ABCD is cyclic, then any of those are true. Alright, doing that last problem, you guys proved most of it. Actually, proving it backwards is a bit difficult to prove that it is cyclic. Yep, so I guess there's 4 parts to this proof, I guess. Firstly, if ABCD is cyclic, then those two angles sum to 180. Second part is those other two angles are equal. third part is if those angles sum to 180, then it's cyclic. Fourth part is if those two angles are equal, then it's cyclic. So try prove as many of those as you can. You guys can get a few minutes. The first two, you guys have already done. Right, the first one I just did, and then the second part is just the inscribed angle theorem. I think that's what it's called. Oh no, it's the angle I didn't know the name of. I mean the theorem. Yeah, this was one of those. So try prove the second two. The second two. Okay, hopefully you guys have had a go at it. Um, okay. Someone asked me if the last one, the fourth one, is just the theorem we learnt. But the theorem we learnt is if ABCD is it's backwards, right? We have ABCD are points on a circle, so ABCD is cyclic. Then we know that ABD is equal to ACD. I think the actual official theorem works backwards, but like the one I said only goes forwards because I never. Yep. Okay, I'll give you guys one more minute. Okay. So we'll move on to slide 9, the Jamboard. I did swap the order around, by the way. In the PowerPoint, this was the first one, second one, third one, fourth one. All right, these are the theorems we learned. All right, the third one, opposite angle sum to 180. I just proved that like a moment ago on the last slide. And this one, two angles are equal. That was the theorem we learned. Like this one, I'm confident that's called the inscribed angle theorem. So now we have these two left. So we'll prove the first one first. So what we want to prove is we have A, B, C, D, and we know that these two sum to 180. Okay, wait. These two sum to 180, which is the same thing. And we want to prove that that means A, B, C, D is cyclic. Okay, so to prove this, we know how to construct a circumcircle. So consider ABC. And then we know the circumcenter, the center of the circumcircle, is where the perpendicular bisectors intersect. You guys don't have to do this, by the way, if you guys write a proof, but I'm just trying to explain that why you're allowed to say you can construct the circumcircle. Because you can't just construct whatever you want, right? Like, I can't say construct line ABC, because that doesn't exist. But we can prove that a circumcircle exists, so that's why we're constructing it right now. So consider the circumcircle of ABC. If it's on D, then we're done, right? ABCD is cyclic. But for the sake of contradiction, let's suppose it's not on D. Then extend line AD until it touches and call that D dash. Okay, so ABCD dash is cyclic. And so that means angle AD dash C is equal to 180 minus angle ABC. But that's also equal to ADC. But then ADC should be, right, because we have a triangle here. So angle ADC is equal to angle AD dash C plus angle DCD dash. But we have this here. So this must be 0. So D dash and D must be the same point. Similarly, for the next one, the second statement, we'll move on to the next slide. It's a very similar proof. Okay, we went through, draw the circle, you see it? Okay, so we have A, B, C, D. And we know that those two angles are equal. Again, we construct the circumcenter of ABC. And it does not intersect C. Instead, it intersects DC at C dash. And again, we know those two angles are equal. And it's also equal to this. So this angle must be 0 degrees. So C dash is equal to C. So ABCD cyclic. Okay, we'll go back to PowerPoint. Here are two problems to try. By the way, cyclic is extremely useful in maths competitions because often problems don't even have circles, right? Like for example, these two problems have circles in the problems. But normally you just find your own circles, right? Because the cyclic quadrilaterals do have quite a lot of useful properties. And it's quite easy to prove if a quadrilateral is cyclic using the two things I just taught. So yeah, they're very useful. The main important things in geometry are similar and congruent triangles and cyclic quads and parallel lines, I guess. That's it. and isosceles triangles, I guess. By the way, it is almost 9 p.m. now, and I'll probably be a bit late. Hopefully I'll finish by 10 past 9. But yeah, if you guys need to go, just let me know. Three more minutes for these two problems. By the way, hopefully these problems show you the importance of having a compass. They are extremely important in maths Olympiads. And just neat diagrams in general. Right, they help you see patterns. And it's easier to prove a pattern that you've noticed than to try find a pattern yourself and then prove it. Because then you know where you want to end up. Okay, so I'll start presenting the solutions. The first part, proving that it's cyclic, is very easy because we have opposite angles that add to 180, right? ABC plus ADC is 180, so it's cyclic. Proving that AC is a diameter, we did do this problem earlier, a similar problem. All right, AOC is double angle ABC or ADC, so it's 180. So AOC is a straight line. For problem 2, we have a triangle, ABC, and we have D, E, F. Right, and then we drew the circumcircles of AEF, BDF, oh yeah, ABC, triangle ABC, and CED. And we want to prove that the circles intersect at one point. Alright, so the way to prove this is to find the point and to prove that all three circles pass that point. And to find that point, we'll define that point as where these two circles intersect. Alright, let's say that's X. And then we want to prove that the circle of CED passes through X. So we want to prove that CEXD is cyclic. Right? We only know two ways to prove that. Either we could do something like CXD is equal to CED, which is a bit difficult. Right? There's a lot of lines that we're adding that have like no relation to anything else. Or we prove the opposite angles sum to 180. Either two pairs work. Right? We can find these two angles. Yep. So the first way would be to prove angle ECD and EXD sum to 180. And the way to prove that is angle AB and ECD is equal to 180 minus A minus B. This is equal to 180 minus A. This is equal to 180 minus B. So this is A plus B. So the two angles sum to 180. Or we could target these two angles instead. That works as well. If this is X, then this is 180 minus X. Then this is X, because this is cyclic, and this is 180 minus X. Then this is X, and this is 180 minus X. And we're done. The other way, proving that like the diagonal angles are equal. Not sure if that's possible. I mean, it could be, but definitely way harder, at least. So now we'll move on to the last theorem of this lesson. And firstly, like the previous theorems, I'll try to get you guys to work it out yourself. Here's two problems. Again, if you guys can't see it that clearly, I'll draw the diagrams on slide 12. The diagram for problem 2 is on slide 13, by the way. I'll give you guys one more minute. Okay, I'll start presenting the solutions since we're a bit low on time. So this was problem 1. DCB is 50. And we know BC is a diameter, so this is 90. We also know there's a tangent, so this is 90. Then we get 40, right, because there's a triangle, and 50, because this is 90 degrees. Next problem. Okay, this problem, it should seem extremely similar to the first problem, and that was intentional. Because now we draw this line, and we know these two angles are equal. All right, so we got 40, 40, 90, because we drew in the diameter, 50, 40. And, right, we notice something. Actually, these numbers are a bit too clean, so maybe it's difficult to notice. But this angle, EBD, is always equal to these angles, right? For any point between BD on this arc, BD, right, point X, BXD is equal to EBD. And that's the last theorem we're learning. We'll go back to the PowerPoint. This is called the alternate segment theorem. Even I know its name, so like maybe it's important to know its name. I don't know. All right, to prove it, it's the exact same thing as problem 2, right? We construct the diameter, and then we know those two angles are equal, and then it's just problem 1. This theorem is actually quite common. So yeah. And now I have some problems. This is the last slide of the presentation, so leave if you want. Maybe remember the problems and try it. Problem 1 is very doable. I will present the solutions, so yeah, if you want to stay for that. Maybe 3 minutes. I'll get 2 minutes, 2 minutes. I'll present the solutions in 2 minutes. Okay, I'll start presenting the solutions. Problem 1, we have A, B, C, D, E. And this is a square, so you know that the sides are equal and that the angles are 90 degrees. And we know angle A is 90 degrees. And O is the center, and we want to prove that AO bisects BAE, so splits into two. So we know that would mean splitting it into 45 and 45. Okay, so there are many ways to find this. First, maybe you want to do some angle chasing. Right, there's a bunch of 45 degrees everywhere. And then you notice that these are also 45. So maybe you try to prove that they're equal. Alternatively, maybe you also find out that these are 90, which isn't that easy to see, to be honest. I mean, it's easy to see, but like, not easy to realize. And then 90, 90, cyclic. So then 45 and 45. So, okay, so since these two angles are 90, we know that ABOE is cyclic. So therefore, angle BAO is equal to angle BEO is equal to 45. And angle EAO is equal to angle EBO is equal to 45. So they're equal. So therefore, BAE got split into two equal halves. Final problem. This problem is by far the most difficult one, this lesson. All right, we have a circle and we have a point P. And we want to prove for any chord, right, which is a line from 2 points on the circle containing P, its midpoint all lie on the same circle. Right, there's infinite chords, and so therefore infinite midpoints, but all of those points are on the same circle. So to approach this problem, right, most maths problems, I mean every problem, if you can, just try some small examples and figure out some patterns. Because once you see a pattern, the problem becomes a lot easier. So we try finding some special chords, right? First, we try the diameter. And this is the center of the circle. And it's also the midpoint of this chord. So we know this point has to be on the circle. Then we also try this chord, right? Perpendicular to the diameter. And we can prove P is actually the midpoint of this chord. The way to prove that is, if we draw the 90 degrees, radii, and this side is common. So then we know by the Pythagoras theorem, these two sides are both the same because we got these two sides are the same and this side is always there. This is always true, right? Oh, the perpendicular to the diameter is bisected by the diameter. So now we know O and P are both on the circle. There's infinite points. I mean, there's infinite circles that contain these points. But logically, it seems like OP would be the diameter, right? I mean, obviously, like, this circle also contains O and P, but it seems quite unlikely. Because, yeah, another reason to think that is because it's symmetrical, right? If we draw this chord, we can also draw its reflection. So now what we want to prove is for any chord, for example, this chord, its midpoint, which we'll call M1, is on the circle with OP as its diameter. There are infinite circles with these points on its circle, but there's only one circle with OP as its diameter. And the way to prove that is because consider its midpoint and construct a circle with this at its center. Right, let's say this is X. There's only one, right? For OP to be its diameter, X has to be its center, and then XO and XP have to be its radii. And then for any point M, right, we'll go on to the next slide to make it a bit neater. Here's point P, here's O. Here is any chord, here's the midpoint of that chord. We want to prove that M lies on the circle with OP as its diameter. And that happens if and only if this is 90 degrees. And this is actually a very similar configuration. This thing, right? And that's because we know M is the midpoint, so these two are equal. And then, very similar idea, these two are both radii. So therefore, since these are 90 degrees by the Pythagoras theorem. Wait, what am I doing? Okay, yeah, it's okay, it's okay. We cannot assume they're 90 degrees. Right, here's OP, here's the midpoint. We know these two are equal. And we know these two are equal. So therefore, these two triangles, we cannot say this. Oh, wait, yeah, then this side is common. So therefore, since these two triangles have equal sides, they're congruent. So therefore, these two angles are equal, and they also sum to 180. So these two angles are 90. So therefore, OMP is 90 degrees. So OMP is on the circle with OP as its diameter. Okay, that's it for this lesson. If you guys have any questions, then you can feel free to ask. But, yep, that's it. Next week, we'll be studying on combinatorics. I don't know what combinatorics means. Just failing. I don't know. Okay, bye-bye.
Thank you. Bye bye.